Okay, we are going to do this little presentation about work and power notes in case you forgot it or didn't get it or needed to hear it again. So what we're going to do is look at work and power. And this is the lecture. It's from Monday, November 28th, the first day back after Thanksgiving. So welcome back, and we're going to look at work and power. And so what I did in class was you're dividing your paper in half. We put work on one side and power on the other, and we're making kind of a two-column, like a T-chart. And we're just going to put a few things down about work and then a few things down about power to remind you from 8th grade or from middle school last time that you had this, what work and power are. So work, the very first thing, we use the word work and we say, oh, I'm going to work, I'm doing a lot of work, or I'm working in the yard, or I'm working on homework, or something like that. And we mean work, but scientifically it has a special definition. So work is done when two things happen. Both of these things have to happen. The force needs to be applied to the object, and the object has to move in the same direction as the applied force. So if I'm applying a force to an object and it's not moving, then I don't have any work being done. It doesn't matter how hard I'm pushing on that object or pulling on that object. If that object is not moving, there is no work being done. So just because a force is applied, it also has to move the object. And the other catch there is it has to move the object in the same direction as the applied force. So here is our formula. When we calculate work, well, we have to look at two things. Obviously the applied force from the definition times the distance that it travels. So think about that. Think about what we just talked about, okay? So we apply a force. Let's say we plug in 200 newtons of force right there, times the distance that something moves. So if I'm applying 200 newtons of force and that object is not moving, I would have to plug in 0 for distance. So my work being done, 200 times 0 is 0. So no work is being done. So mathematically, it's even proven there. The triangles to the side, work is equal to force times distance, and then you can use that triangle to solve for any other. If I'm looking for the force, remember I'm going to cover up the force, and that would be work divided by distance. If I'm going to study, or if I'm looking for distance here, I'd cover distance up and it'd be work divided by time. So let's move on to units. So whenever you are doing your problems in science, you have to put your units on them. So these numbers are coming from something. Something's happening. We're talking about work. We're talking about you're applying force somewhere and you're moving an object, or you're not moving an object, and we're seeing how much work is done. So the unit for work is a joule, J-O-U-L-E, and it's abbreviated with just a J. And that's named after, I think his name was Richard Prescott Joule. I believe he's the one who did the fundamental calculations and kind of set this up. So we call a Newton meter a joule. So that's our work. And so again, a Newton meter is a force of a Newton times a distance of a meter. So if I move use 1 Newton of force and move an object 1 meter, accelerate that object 1 kilogram per meter per second, I get a joule of work. Okay, so those are our units that we have to use. Work, and we've said this before, just write it down in your notes, and this is the last thing we're going to put for work. If an object is not moving, work is 0. So you don't have any work done if it's not moving. Now, power. Let's flip on the other side of your sheet where on your T-chart you have a side for work, and now we have a side for power, so we're switching over to power. And power has something to do with work. It has to do with how powerful I can do that work, how fast I can do that work, the rate at which work is done. So in my own words, we put that as how much work is done in a given time. So if you, we use the example of raking the yard. If I rake the yard, I don't have a very big front yard, but it might take me, an hour to rake all the pine straw out of the front yard into a pile. But if I have a leaf blower, I have more power. So I can do the same amount of work. I can move all those pine needles to a pile, but it only takes me maybe 5 or 10 minutes with a leaf blower, whereas it's going to take me, an hour with just a rake because I have more power. Engines in cars, the same thing. If you have a more powerful engine, you can move faster You can move the distance faster, move the car faster, accelerate faster. You can pull a heavier load if you have a more powerful engine. So if I have more power, I can kind of do more work or the same amount of work in less time. So that's what powerful is. And here's how we calculate power. Power is work divided by time. So if I set that up, I can rewrite it as work is equal to power times time. So when I place it into my triangle, if you wanted to use the triangle over there, work goes in the top, power and time go on the bottom. So you can definitely see that. All right, and our units for power are the watt. Whenever I have power, it is a watt. So it is 1 joule of work, because remember joule is the unit for work, per second. So per 1 second. Time is measured in seconds, the SI unit. So 1 watt of power is the equivalent to the same thing as a 1 joule of work being done in 1 second. So those are our units for power. So this is the end of the presentation. I'm going to use the next presentation listed here on Google Classroom to show you how to work out some problems. So if you needed to see some examples of actually how to work out the problems, look at the next video.